Hello. Hello. Oh, you can hear me now, can't you? Let's see. Testing 1, 2, 3. Well, I can't hear anything yet. Looks like it's going out. Why would I not be hearing it? That's working. Why would I not be hearing it? There we go. All right, so it is working. Okay, so just to be clear, I do not believe the Inmendham deflection theory, but it's pretty clear what it is. There we go. So I'm going to go through my mathematics. All right, so it is working. From scratch, excuse me, from scratch, more or less. Okay, so speed of Earth around Sun. We go around the Earth every day. That's, at the equator, a couple thousand miles an hour, if I recall correctly, and I might not. But we go much faster around the Sun. We do that every year, so we can be really confident that's happening. So 30 kilometers per second. Okay. And then let's say the speed of light. Meters per second. So that many meters per second. This is 30,000 kilometers, 30,000 meters per second. So this number divided by 30,000 to get the fraction of the speed of light. Oops. This is live math there. So it's 1/10,000th, right? 1/10,000th, just to round it. Oh, I see. Let's just do that. Now that's the speed of the Earth around the Sun. Okay. Lots of ways to measure that. Lots of ways to just measure the circumference of our orbit and divide by the year. So 1/10,000th. So a mile, 1 mile in feet. All right. Right. So what's 1/10,000th of that? 5280. I know I shouldn't memorize 5280, but I would have just done 5,000. That's not right. Divided by 10,000. That is 0.528 of a mile, so 0.528 a mile in inches. Oh, I'm getting ahead of myself. No, I did that wrong. No, that's right. Oh, I'm sorry, that's how many feet it is. Oops. 6 inches. So over a whole mile. Okay, so I was getting ahead of myself. So Gary, I think you did do the math wrong, but it's not necessarily wrong. It's just when you do this, the napkin math, you're just getting an order of magnitude. The point is, we're in earthly realms, both of us agree. They used to say that if astronomers agreed to a factor of 10, they were right on. So, so here's the thing, though. Think about it. So you said it before, and so this is what we can rely on. This is how it would work based on what you're saying. The laser shoots up, but the mirrors are going half the speed of light. So by the time the thing is up here, whatever the width is between the laser on one mirror at one mirror or whatever, and the other mirror, by the time the light has gone that far, the mirror will have gone half as far because the mirror in this case is going half the speed of light. So that's how it works. If the mirror's velocity is a tenth of the speed of light, then it would bend it so that this distance here is a tenth of the distance it's gone. Whatever the distance. If the light has gone a foot, then the mirrors will have slipped by a tenth of a foot if it was a tenth. Okay, so it's not a tenth. With the speed of the Earth around the Sun, it's 1/10,000th, which, as I just went through, I guess is 6 inches. And please correct me. I mean, I'm doing this live, you know. And I'm still going to do it some more and redo it because there's a bigger velocity to rely on. So that's 6 inches over a mile. So let's do that really quick again. We agree that the speed of light is these 300,000 meters a second, and the speed of the Earth around the Sun is 30,000 meters because of the kilometers per second. So that is definitely 1/10,000th, roughly 9,000 something. So if the light is going a mile, we can divide that by 10,000 and find out if how many this mile is. 5,280 feet divided by 10,000 is half a foot. So we got 6 inches. So in a mile it would deflect 6 inches. So let's take this. In a half mile it would deflect 3.1 inches. In a quarter of a mile it would still be deflecting an inch and a half. Okay, in an eighth of a mile it would be 0.8 inches. Eighth of a mile, 1/8 mile in feet. 660 feet. All right, so that's the calculation for that. However, there's another thing. Speed of solar system around through galaxy. And here they're telling us it's a 13,000th of the speed of light. Right, so I'm not even going to calculate that. The Wikipedia says it's 13,000th of the speed of something. I'm sure it's light. Yeah, 1/13,000th. Okay, so that means that over a mile's worth of feet, we're going to have how many feet of deflection? 4 feet of deflection. That's 4 feet of deflection over a mile. And let's say it's a quarter mile. Let's say it's a 16th of a mile. Or actually, let's not even do that. Let's do this. Let's just say you can do it 50 feet. 50 feet. 15/32 of an inch. So that's about a half an inch. A little less than a half an inch. So over 15 feet, a laser will move a half an inch from the deflection of our speed through the galaxy. Just over 50 feet, right? So 100 feet, it's going to move a whole inch almost, right? Redo the calculations. I'm showing you because I don't care if I got them wrong. The gist of it is let's figure out what the prediction is, because we're already finding its real world macroscopic values. Because here's the thing. When the Earth rotates every day, right? So that means at one point in the day, we're shooting along in this galactic orbit, right? And we're on the side of the Earth where our velocity is this way, to the side, right? So we're getting maximum deflection according to the Inmendham effect in the other way. Whereas 12 hours later, we're on the other side of the Earth. Okay, so we're getting it this way. We have our apparatus there pointing, we're pointing our laser here way 90 degrees to the velocity. We're getting the maximum deflection, right? And then we rotate around the Earth, but the velocity stays in the same direction. So 12 hours later, instead of pointing this way, let's say it's west, it's going to point this way. Say that's east, whatever, whether I got it wrong or not, right? So the deflection is going to be in the other direction. So we know the thing's going to move back and forth. And I'm saying because we're on a curved surface and the velocity is going to come at us at weird angles, in between there it's going to take an arc. And on the way back it's going to take the opposite arc and it's going to make an oval, otherwise known as an ellipse. Maybe some deformed elliptical kind of a thing, because I didn't do the math that exact, but it's going to be like an ellipse. And if it's going to move over 50 feet, with just 50 feet away, if it's going to move a half an inch radius, it's going to be a whole inch. Now, to get lasers to go really far, you need a big fat beam. I was researching this. Over 50 or 100 feet, you could probably do with a regular old pen laser. And the point is that you just leave it on for 24 hours. Powerful lasers that can shoot a mile can't necessarily stay on 24 hours. They overheat. So that was an issue. But with this galactic speed, even a regular laser, and you want to mark the center, but the dot might get pretty big at 50 feet. It might be a couple inches big. But even if you did the circle, you should be able to see it move around. Okay, and so that's the math as I see it.